Hey, I've been thinking a little bit, just kind of about some history about the Jacobi elliptic functions, which they're directly responsible for the name of two things that people study now. I mean, well, they kind of came from elliptic integrals, so they're not really responsible for that, but it's very similar. Uh, if, if you see elliptic integrals in Calc 2 or something, they ask, well, what does these have to do with ellipses? They say, well, it's something like the perimeter of an ellipse, but that's kind of all you hear. And then they definitely influenced what is now called elliptic functions. And at first glance, what does elliptic functions have to do with ellipses? Kind of absolutely nothing. And likewise, this is an analysis. In algebra, they led to something that is now called elliptic curves. And so just real quick, what is an elliptic function? It's a doubly periodic meromorphic function on C. You say, okay, what does that have to do with an ellipse? Well, on the surface, absolutely nothing. Same thing, an elliptic curve. It's a curve that looks like, well, you can always write it in the form y squared equals p of x, where p, you can actually take it to be a polynomial degree 3, but it can either be degree 3 or 4, and it'll still be an elliptic curve. So what does something like that have to do with an ellipse? Well, again, on the surface, absolutely nothing. So why did these get called elliptic functions? Why did these get called elliptic curves? Well, the reason is because Jacobi invented a trigonometry based on an ellipse rather than based on a circle, or we also had hyperbolic trig by that point. So they had already developed trig based on a circle and trig based on hyperbola. So he's like, well, what happens if you try to develop trig based on an ellipse? And he came up with a really beautiful theory. And it turns out that the functions involved were doubly periodic meromorphic functions over C. And so those became to be studied in their own right, and they were called elliptic functions. And it turns out that every elliptic function satisfies a differential equation that looks something along the lines of derivative squared is polynomial in the function itself, where p is a polynomial degree 3 or 4. So because all these elliptic functions satisfied this differential equation, that led to people really looking a little harder at these curves. And so they came to be known as elliptic curves, even though, I mean, that equation has absolutely nothing to do with an ellipse on the surface of it, but it came from, again, Jacobi trying to make a trig based on the ellipse. That led to the discovery of elliptic functions in general, which they're just called that because these are examples. What they are is they're doubly periodic functions. And it turns out these doubly periodic functions all satisfy a particular form of differential equation. And so if you take the algebraic analog, that became known as an elliptic curve. And both of these are very, very important today. If you've dabbled in recreational math, you've probably at least heard of Andrew Wiles' proof of Fermat's last theorem. And it relied very, very heavily on trying to understand semi-simple elliptic curves. And so, yeah, but we're not going to go anywhere near any of that because, for one, I'm not an algebraist. I mean, I do not. So I can tell you quite a bit about the elliptic function side of things. My knowledge of elliptic curves is pretty sparse. But anyway, just because these have kind of been lost in the process, because when you start studying elliptic functions now, so again, elliptic functions now, well, you start with the assumption, okay, this is something doubly periodic. And if you start with that being your goal, the most obvious example is something called the Weierstrass function, or rather, the most obvious is its derivative. And then you integrate it to get the Weierstrass function proper. And those two are kind of the basis for the way people study elliptic functions now. So, which this is a very beautiful picture, and I want to talk about it. So I am going to record one video just on the Weierstrass function and its derivative, just because if you want to doubly periodic functions, by all means, that's the way to go. But the Jacobi functions originally, where they came from, I'm just going to give a real brief history, and then we'll save this for later. So trig, of course, in the ancients, the name trig comes from the study of triangles, but modern being the last several centuries, it's really the study of a circle. So by definition, if I go angle theta here, theta is measured in radians, which we'll actually need to talk a little bit about that. Then by definition, the point is cosine theta sine theta. And after they developed all these wonderful circular functions, which the importance of the circle is it is the unit locus for the standard Euclidean metric. So if I just say distance squared is x squared plus y squared, you get the unit circle for being everything that's distance 1 from the origin. Well, then they said, well, what about if you change this and you say distance squared is dx squared minus dy squared, which today this is called Lorentz geometry, because it came up in physics in the study of special relativity, or what would become special relativity is based on this this metric where one of the signs is different. Then your unit locus is a hyperbola, and if you measure this angle in what are used to be called hyperbolic radians, I haven't found that in a book in a long time, but they used to say that. Then this point would be cosh and sinh. And that's going to be one of our points, is that the way we measure angles is going to be a reflection of the type of geometry we're doing. So the radian measure we're used to is really geared for doing Euclidean geometry. If you want to do Lorentz geometry, then your angles between these directions that have different signs, you should really measure them in hyperbolic radians. And so Jacobi asks, well, can you do the same thing if you start with your ellipse as being the basic shape in your geometry? So he took that to be length 1, that to length B, and said, well, can you create a trigonometry based on this ellipse? And sure, you can. So if you measure this angle, which I'm going to make up a word here, but I think it's a word that should exist. If you measure this angle in elliptic radians, then by definition, this point here is Cn of u and Sn of u. All right. And so we get a theory that reflects just regular trig. These things are obviously periodic because, well, whatever the right angle is, so we usually say K is the measure of a right angle. in these elliptic radians, then these two are obviously periodic. Periodic with period 4K. A lot of times K is called the quarter period because of that. Of course, for a circle, K is pi over 2. And so circular functions, 4 times pi over 2 is 2 pi. They have period 2 pi. Well, it winds up that as Jacobi studied these and extended them to a complex argument, he found that if you, actually, let me see. So if this is, if the eccentricity of this ellipse is epsilon, then I'm going to say epsilon prime is 1 minus it, kind of the complementary one. The eccentricity of the complementary ellipse. Then what winds up happening if you do one of these Jacobi functions an imaginary argument, well, just like for regular trig functions, you wind up pulling the I outside, and then you get a hyperbolic trig function. The same thing's going to happen here. If I build my Jacobi function with a eccentricity epsilon, and then put in an imaginary argument, I wind up, the imaginary argument comes out for sine because it's odd, but I get, I think it's actually SC instead of SN, but I get the complementary ellipses trig function at U. And so this leads to a really interesting thing though, because this guy is periodic with period 4K prime, right? Which means that two things are going to happen. Not only are we going to have this initial guy is periodic with a real argument, it's also going to be periodic with an imaginary argument. So this is where the double periodicity comes from. It comes from the fact that okay, I can't spell periodicity apparently. Periodicity. Okay, it comes from the fact that if you plug in the imaginary arguments, you get this complementary ellipse. This complementary ellipse is also basically round, and so it has its own period for its trig functions, as opposed to the regular trig functions. When you put in an imaginary argument, you get functions on this hyperbola. The hyperbola is not round, and so these guys are not periodic. So your regular trig functions, this second periodicity is kind of degenerate. I mean, it winds up, these are sort of periodic with period infinity in some sense. So that's kind of a silly period to have. And so for regular trig functions, the second period degenerates. But if you go to an ellipse so that the complementary shape is also an ellipse, then the second periodicity actually is a real thing. And so you get these doubly periodic functions. And so that's how the history went. It's Jacobi wanted to develop trig based on your fundamental shape being an ellipse. And then he noticed that if you put in a complex argument, you get geometry on a complementary shape, which is also an ellipse. And so it turns out that his functions were doubly periodic. And then after that, they started studying double periodicity in its own right, which led to Weierstrass. And then once they did this, it turns out that all these things satisfy those different equations, which led to what were called elliptic curves, which I'm not an algebraist again, but as far as I know, it's completely a coincidence that these curves that come from the differential equations of double periodic meromorphic functions happen to be exactly the genus 1 curves in algebraic geometry. So if you know a little bit about algebraic geometry, genus 0 is the conic sections, which from an algebraic geometry standpoint really is just the circle. I mean, they're all the same. So it's like, what's the next hardest thing you might study? Well, it's genus 1. And it turns out that everything genus 1 are these curves that come from the differential equations of double periodic functions. So anyway, that's where the names of these other two things come from. And I thought it was kind of tragic that these Jacobi functions, even if you study algebraic geometry and study elliptic curves, or if you study complex analysis and you study elliptic functions, you may never actually see Jacobi's elliptic trig functions. And I just thought that was a tragedy. So I wanted to record a series of videos on it. So hope you enjoy them, and we'll see you in the next video.